Next speaker is Heino FALCKE, and they will tell us about the imaging black holes now and in the future.
Okay, good. I can be heard. Great. Thanks for staying around and listening to the next presentation. You heard on Tuesday how you can actually listen to black holes with gravitational waves. I'll try to tell you how you can actually image and see them with radio telescopes. That's part of the global Event Horizon Telescope collaboration that is going on right now. But of course it has a longer history and has a long future, I hope. My own group is funded largely by a very significant ERC synergy grant together with other groups in Europe, Luciano Rizzola, Michael Kramer, also working with IRAM and the VLBI group in Bonn together. So we slightly biased to some of the things that we do. That actually program funds a lot of the theoretical work that I'll show, but also a lot of the experimental parts of it, so a lot of the VLBI equipment that's going to the telescopes, and also some of the data analysis that we're doing. So it's actually a fairly comprehensive program. Now let's go back and how is our picture actually of how black holes look like. And the first image I can actually remember or found is this one by Cunningham-Bardeen, looking at how actually a star orbiting a black hole would look like. And that is still resonating today. If you look at Hollywood movies, you find pretty much the same structure still. So what you're seeing there is mainly, I think, the structure of the accretion flow that's actually gravitationally lensed by the supermassive black hole. The paper that sort of caught my interest when I was looking through actually conference proceedings, because that is a paper that is in a book where the paper by Novikov and Thorne is, which has like 500 citations. That paper had like 20 citations, which was sort of a few pages later. But actually that discussed how a black hole would look like that passes in front of a star. So the idea is you have a binary system with a black hole and the star, and then the black hole passes in front of the star, and then you could see actually how the black hole looks. And what you see here is really the light disappearing in the event horizon. And that actually gives a very sharp feature. And that is coming from the photon orbit that you have around a black hole. So you can have actually a closed orbit where photons in principle could circle for an infinite amount of time. However, that means if you're an epsilon too close, they'll actually end up, these are 4 light rays, 2 will end up in the black holes, 2 epsilon bigger orbits will actually escape to infinity. And what's important here is that that feature that you see, that black hole that you see in the star, will actually be pretty large. It will be 5 Schwarzschild radii in diameter, even though this is actually an extremal Kerr black hole. And the reason is that with an accretion disk, you can go very close in a matter on orbit of about like half a Schwarzschild radii orbiting a black hole. But the photons go both directions. So on one direction, they go actually with the spin, they go very close, but on the other side, they go against the spin, and they're caught much further out. And so the image that you see is actually fairly large. It's 5 Schwarzschild radii. And that was something that people sort of had a bit overlooked when they were discussing how big black holes would appear. And that actually made a crucial difference later. There were other papers, very famous, Luminet, which actually almost did the same here, illuminating a black hole from the back. And then this famous picture here showing, again, this accretion disk, which is hand-drawn by computer-generated. So, computer-generated, and then he drew it with hand. I'd still argue that this largely shows the hole in the accretion flow and an image of the inner ring of the accretion flow rather than the black hole itself. But of course, this is how we picture quasar accretion disks. Now, it turns out we're actually maybe not looking at quasar accretion disks or black holes first to actually see a black hole. We're going to look at low luminosity black holes, nearby supermassive black holes, which then have low accretion rates and low powers because quasars typically far away, and so their shadow size will be very small. This is the center of our Milky Way. You've seen that probably multiple times. This was a radio picture And then this was a picture of the VLA zooming in. Into the very center, you have Sagittarius A star, the compact radio core in the center of the galaxy, which at some point was then, labeled Sag A star, Sagittarius A star. And that was always suspected. People like Rees and others, said this should be really there should be a radio source in the center of our galaxy, which should mark a supermassive black hole, if quasars are also supermassive black holes. And so that source was found. It's very compact. And of course, the stars were found orbiting this radio source. And we know from these observations they are 4 million times the mass of the sun concentrated in that radio source, which is in the center of the galaxy. And now, actually, the gravity experiment at the VLT is now measuring, or has measured, the passage of this star S2 for the second time. And this is a brilliant, brilliant experiment if you see those results and that they're having, or will come out soon. Now, I got into this game trying to explain the radio spectrum of Sagittarius A star, which is quite telling. This is a frequency, this is intensity. And what you see is that the radio flux actually rises, and then suddenly stops, and there is sort of a maximum frequency where the radio emission goes to. It's a flat radio spectrum. There's actually a simple back-on-the-envelope way to explain these things, and we did this essentially back on the envelope indeed. The idea is, in this picture that we have today, and this is sort of a second important aspect of this, that namely the accretion flow in low luminosity systems is radiatively inefficient. So it flows to the center in a thick disk, but it's optically thin. Then in our view, a picture model, the radio emission is actually made by the outflow, by the jet that leaves the system. And in fact, essentially all black holes that we see radio emission from, we see jets associated with this flat radio spectrum. Sag A star, we don't see it, but that has to do with scattering, I would claim. I will come to this later. The basic idea is you have synchrotron emission here. The jet goes out. The density decreases in a well-defined way. Again, you can calculate this back on the envelope. And then the spectrum or the emission at lower sections or more distant sections from the jet will actually go to lower and lower frequencies. That gives you the flat radio spectrum. And what you also find is that if you go to the highest frequencies, the emission will come from near the black hole. So if you go to 230 gigahertz, the emission should come from really within a 1 or 2 short-shoot radii. That was sort of the simple calculations. And in fact, if you do fancy GRMHD calculations today about jets, and you actually recover the simple basic scaling laws we had in the 90s and earlier. Now this then led to this paper here, where we actually wanted to know, okay, if we now have radio emission, which engulfs the black hole, not coming from behind, but really engulfs the black hole, and you have an optically thin fog essentially around this black hole. What would you see? And it turns out you actually see the same feature again, which we then call the black hole shadow, which is 10 gravitational radii, and that in the center of our Milky Way, at the distance of Sagittarius A star, would be 50 microarc seconds. And that's an interesting number, because being at a radio interferometry group at the time, it was clear that a global VLBI array at that frequency, when you have radio telescopes distributed over the Earth, would have a resolution of actually better than 50 microarc seconds, would be like 20, 25 microarc second resolution. So you have actually a frequency where emission comes from the center of, from near the event horizon, and you have a technique which was established at the time that would be able to resolve it, but didn't have yet good enough image quality. Now, lots of papers appeared thereafter actually looking at variations of the shadow. I mean, if you have alternative theories, more parameters than just the basic Kerr black holes, we have scalar parameters, dilaton fields, and whatnot. They all actually add then to the complication of the image. So different theories of gravity will obviously give different appearance of shadow. So this is something that in principle you could test if you have high quality images. Turns out there's another source which actually gives us almost the same opportunity. This is M87, which actually was the very first black hole that was actually seen, because around the time that Einstein was doing his general relativity, there was an astronomer seeing a little streak in this nebula, which nobody knew was a galaxy at the time, but there was a streak. And also nobody had an idea that this actually was coming from a supermassive black hole at the same time that the basics of general relativity was laid. But so there was a theorist and an astronomer who had no clue that we're doing something which was fundamentally linked at a very, very deep level. Now this has a more uncertain mass determination. There are two different ways to determine it. But it has a beautiful jet that extends. It's 1,000 times more massive, actually 2,000 times, 1,000 times more distant, so the shadow is more or less the same size. And the combination of mass and accretion rate actually makes it that the event horizon frequency, which is mass and accretion rate dependent, if you use these basic scaling laws, also is roughly at 1 millimeter wavelengths to 30 gigahertz. So it's just pure coincidence that both sources are in principle equally useful, though this will be less useful for testing GR because the mass is less well established. So it may be useful to make images and see the shadow, but testing GR will be more difficult. Now we have a much more advanced set of tools to actually help us in doing the simulations and also reducing the data, obviously. And I just can't go in each of these sections is a talk in itself, could be a workshop in itself. A lot of codes now available to do plasma simulation, general relativistic magnetohydrodynamic simulations of gas. And we have developed one, but there are others, a bug code, which has ideal GRMHD, three-dimensional, multiple coordinate systems. And what's special about this one, it has adaptive grids. It can also do arbitrary spacetimes. So we can do alternative black holes as well. If you give us a metric, we can simulate accretion flow in that alternative metric. Ray tracing codes, there are also multiple of those. The one that we developed is Raptor here by one of my students and Monika Moshi-Bratska in our group. It also can do arbitrary spacetimes, synchrotron emission, absorption, polarization, Faraday rotation. So really gives all the predictable parameters for radio observations. Then we have VLBI simulators. You want to actually a detector simulation. You want to predict what your VLBI array, your interferometer will actually see. And there's a recent development from McSilhouette, Roger Dean, that works with us he's actually in South Africa, which has a lot of physical effects, tropospheric fluctuations, pointing errors of the telescopes, the actual observing schedule you feed in. So this is actually the most advanced VLBI simulation available now, and actually only since a few weeks. We have an automatic VLBI calibration pipeline, so you get the simulated data, you pipe it through an automatic pipeline which will calibrate the data, and it's the same pipeline that will actually also take the real data. And there are multiple imaging algorithms. There's a big industry of testing many imaging algorithms on this calibrated data. Maximum entropy, EHD imaging, and Chael is actually here at this conference. And in fact, there's also a big effort to compare those codes, the different GRMHD codes, the different imaging codes, and so forth. So then that's actually nice because it brings together different groups which usually do their things independently. They're now actually checking their codes and comparing those things against each other. Now, again, these are simulations that Monika Moshi-Bratska, of the Sagittarius A star, which is a GRMHD model, three-dimensional. It includes, it actually fits the spectrum and the size of Sagittarius A star quite well, also at low radio frequencies. This is how the source would look at 7 millimeter, at 3 millimeter, and 1 millimeter. This is 230 gigahertz, this is 43 gigahertz. There is scattering in the galactic center. There is some annoying molecular cloud at around 3 kiloparsec from us, which is ionized by stars, and has sort of some turbulent ionized plasma, which actually corrupts the wavefront. So it actually scatters radio waves. So at low frequencies, all you can see is this blob. And if you go to 3 millimeter, it's still a blob. If you go to 1 millimeter, the scattering becomes small enough that actually not only the emission comes on the event horizon, the scattering becomes just small enough. So this is also a coincidence. It's pure coincidence that these two effects actually become small enough at 230 gigahertz that you actually would be able to see the shadow, and that the Earth has just the right size that you can build a global interferometer, that you can actually have a beam that is actually smaller than the predicted shadow size. So these are three actually independent effects which have nothing to do with each other. They just nicely conspire at this sort of magical frequency. Now, VLBI, we've heard actually this nice talk about Ryle on, I think, a Tuesday. and who actually invented he was not the only one, but he sort of made major contributions to establish long baseline interferometry. This is standard these days since more than 40 years. A lot of observations were made with the VLBI. Kudos to that. At lower frequencies, at higher frequencies, no standard array exists, so you have to use sort of single-dish telescopes. The very first detection of Sagittarius A star was made in the middle of the 90s of the last century by the Bonn group, combining Noema in France and Pico Valeta in Spain. They made a measurement, they detected Sagittarius star, they made a mass measurement. It was sort of taken with a bit of criticism at the time. Turned out that actually, because their size was pretty large in Schwarzschild radii, but actually since then the black hole mass has grown by a factor of 2 due to improved measurements. I assume it's probably not grown that much physically. But, and so that measurement actually was quite correct within the error bars with what we think today the measurement at 230 gigahertz showed. A better improved measurement was then made with a triangle of telescopes, which is a more robust way of measuring this in the US, which actually really confirmed the basic size. The most latest measurement that is public is now with 4 stations, including the Apex telescope in Chile, which is standing right next to the ALMA array. If you look at the measured sizes with these VLBA here, this measurements we made, and here Shin and Rogers et al. At 3 millimeters, and then later, in fact, 1 millimeter was first, and then later here the Dolman et al. Result in 10 years later. This is the intrinsic size measurements that were made, and they all point to the fact that indeed, as predicted, as you go to higher frequency, the size of the radio source becomes smaller and smaller and approaches the shadow size at 230 gigahertz. This is the turnover point. And so that's the magic frequency you have to look at. Now, what is the structural information available at these highest frequencies? Now, what you measure with VLBI, and I think we heard that also in the talk on Tuesday, or was it Monday? I think it was Monday. That what you measure actually on each baseline between 2 telescopes is actually the Fourier component of that image. Yeah, ideally you want to measure every Fourier component, and the longer the baseline is, the higher frequency Fourier components you measure, the higher the resolution. Okay. Now, if you only have a few baselines, you only measure a few Fourier components of the image, and then you have to, in your head, you have to make either a model or an inverse Fourier transform to get to the image. So what you see here are the measurements at different baselines. So these are longer baselines here, different telescope combinations with the 3-element array. There's a short baseline and then long baseline. What you see actually here, a Fourier transform of a disk, a Gaussian disk. Well, Fourier transform of a Gaussian is a Gaussian, so that is easy. If you have a ring, what you hope to see at some point, you would have a null in there. So that looks quite tempting here, that you actually, this seems to indicate that there is some, this is not a Gaussian disk, or that there is some structure. The recent paper, which is, I think, now it's either in press or already published, we had, shows now more and longer baselines, and indeed, sort of the overall picture really looks like sort of ringish, diskish, ringish. However, you have to be careful because this measures only a very narrow range in sort of our angle over the source, because that is not a full 2-dimensional Fourier transform. This is sort of a 2D image to a 1D plot. And so you can easily explain the same data with 2 models, one with a ring, or shadow-like, so to speak, and the other one with sort of 2 blobs next to each other. What is important, along this axis, so to speak, these 2 images pretty much, equivalent. So with this limited UV coverage, which is still the best we have published so far, it's not possible to distinguish between these two models. What? Yes. At 20 minutes? Okay, at 35. Yeah, close. Okay. Well, okay, then you're not going to see the rest. No. So we had an observation in 2017 with 6 telescopes and 8 telescopes on 6 mountains. In 2017, so the largest range of baselines. This was actually a miraculous observing run, and it was miraculous because it was good weather for 6 days over the entire world. So this hardly ever happens. And so the data really, it looks excellent. These are the telescopes, these are the institutes involved. This is the current timeline of things that's going on. That's perhaps interesting. There was the observing run in April. Only in December 2017, the data from the South Pole telescope actually arrived. So in the beginning of this year, we had correlation calibration of the data. There are actually 3 different calibration pipelines that are being used to calibrate the VLBI data. 3 different groups are doing this. Beginning of last month, the first data was released to the imaging teams. So there are now 4 independent teams imaging Sagittarius A star and M87, and they don't talk to each other. So in July, we'll compare the images that we have with each other, and then we hope to come to a consensus result. And then later this year, we release this to the science data groups, and then hopefully the publication will come out in early 2019. What can you expect? There are certain problems that you have. One is that the source Sagittarius A star is variable, and the second one is that the scattering screen actually moves and is sort of patchy, moves over the source. So it could well be that for a single epoch, what you would see is sort of just some few ugly blobs, some structure, but it's difficult to interpret. What you then have to do is to average over multiple orbits, of course, and over multiple weeks, different realizations of the scattering screen. So then you would get something like what I call an ugly peanut, and hopefully it becomes a more beautiful peanut at some point. M87 is perhaps more promising in a way, because these are simulations that Monica made here, very nicely reproduces the jet. And we don't really put the jet in there, right? It comes out automatically in these simulations. And this is a simulation at 230 gigahertz. And on the right, this is a simulation made with the best VLBI simulation we have right now, feeding in the actual schedule that you would use, feeding in the actual configuration of telescopes, pointing errors, and so forth. And you see actually a nice ring here. This is, in fact, the photon ring, the shadow in the middle, and you should be able to recover a photon ring if nature cooperates. Of course, there are complications. This here is a movie, and this is the photon ring that you see here. This is actually over a couple of months. And then look at this frame here. For a couple of weeks, you actually see a ring which is actually larger than the photon ring. Why is this? Well, there was a blob in the jet going behind the black hole, and it produced an Einstein ring, which was twice as large. And the uncertainty in the black hole mass is also a factor 2. So it's going to be interesting to distinguish between those 2 possibilities. Of course, those blobs, those Einstein rings, they disappear, they're temporary. So it's actually, you can do this by doing multiple observations and confirming this. It will be quite interesting to do this. Now, this is a simulation which just, I think, appeared yesterday, was actually even on the cover of Nature Astronomy. These are simulations, really full simulations of a black hole accretion and ray tracing, ones in a Kerr black hole and with a dilaton black hole. Now, we purposely tweaked the parameters such that the dilaton black hole would look similar to the... someone is calling you? Or someone else? It's not me. They would look, pretty much similar. And indeed, if you simulate the 2, the Kerr black hole and a dilaton black hole with the current resolution looks relatively similar. So it may be difficult to rule out all alternative theories of gravity. Now there are some, I'll go quickly now, some future developments. More telescopes will join on shorter baselines here, Kitt Peak. The Greenland telescope has joined in 2018. Unfortunately, we had pretty bad weather in 2018, so data will not be quite as good as 2017. Noema in France will rejoin the array. We're funding some upgrade here to do a phasing, so that will improve this. I'm involved in a project. We're trying to get a telescope into Africa, actually move a telescope from Chile to Africa there, which is not a huge investment cost to do, and we're still open for partners to join if you're interested. Talk to me afterwards. And then actually you could get something like this where really a nice shadow is visible with a full array, including Africa. So then we can really do precision tests of GR with this. Now, finally, the last step in the future, obviously, you want to go to higher frequencies. Higher frequencies means less scattering, means also higher resolution and more concentrated emission. This is 230 gigahertz model with scattering. This is 690 gigahertz emission. And this is with scattering. There's hardly any scattering left anymore. Problem is 690 gigahertz from the ground is almost impossible. I mean, there are 1 or 2 sites in the world where you can do, observe at these high frequencies. The troposphere really is giving you a lot of trouble. What we're proposing is actually a space interferometer. Actually, you can do this, we show this with just 2 antennas, 2 satellites, 4-meter diameter, which are at 15,000 kilometers above the Earth's center. They rotate and they drift apart slowly. That gives you all combinations of baselines. You have short baselines first, long baselines, and they rotate, so really cover the Fourier plane completely. And that's something that's actually doable with more or less today's technology. You have a laser link in between. You have used GPS to actually determine the orbits better. This actually, images you can actually get really razor-sharp images of the event horizon if you build such an array. Of course, you first want to see the actual results on the event horizon telescopes, but there's a lot of future and potential for actually making more and more detailed tests in the future. So let me conclude. Images of black hole shadows are, I think, no longer pure fantasy. Actually, this is really happening as we speak. We have really a comprehensive tool to model black holes. The good thing about low luminosity black holes is they are simpler. They're much simpler than quasars because the accretion rate is low, density is low, and so there's less dirty astrophysics involved. We'll deliver first results, likely early 2019. Don't expect maybe too much. It'll be rudimentary at first, but still I think pretty exciting and fascinating to look at. And the images will become sharper with time, multiple epochs, higher frequencies. We can go to, 1 higher frequency still in the EHT. We can add France, Africa, essentially space. It would be great to find a pulsar in the galactic center. A group of Michael Kramer is looking for this. Certainly the stars will help us to constrain the mass of such a star better, and also hopefully the spin at some point. So we have, like cosmology, we have multiple actually experiments that zoom in. And of course, the great thing is Sagittarius star and M87 will stay around for centuries to come. There will not be a bing and they're gone. They'll stay there, and we can measure them and improve the experiment for next decades. Thank you.
Thank you. A very beautiful talk. Sorry about pressing about time.
That's good chairman.
But you talked about for 27 minutes and 16 seconds, so it's pretty good.
Yeah,
so, questions? Yes. Let me give you this microphone.
Just to play devil's advocate, how do you know that you're not looking at some jet feature? And what is the level of the systematics compared to this little peanut shape? So 2 questions, actually.
No, I think that's exactly a great question. I think the only way to be sure about this is to have multiple epochs, because any jet feature will actually move out, right? In M87, the time scales is actually weeks, days to weeks. In such a star, the time scale is 20 minutes, so actually already orbiting about a lot of features within one observing run. Still, you need multiple years to do this. So I think that's, I think with one image, I think even though it's going to be exciting, you're not going to be 100% sure this is not an Einstein ring, for example, that happened to be there just in fooling us. So yeah, patience is always with science. That's how you do it.
Okay, so any more comment? If not, actually, I have a question about the closed pulsar. So what do you mean by closed pulsar would be great?
Well, we have now the magnetar that we found, which is a 200,000, well, a few 100,000 M. That's not a good pulsar because it's sort of irregular. It's a magnetar. You'd like to have something which is on orbits of, ideally a year, but tens of years would also be great. And then you can measure the space-time. And the good thing about the magnetar is that it shows pulsars can exist in the very center and have been formed. So there should still be some there. And Rafe Etoff is here. We've actually been searching for them. So there's an active program now to look for them. And we have only really started to scratch the surface in a way, because it's, it's not so easy there. Certainly SKA, for example, may make a big difference there.
Yes, there is
At higher
one more,
frequencies.
yes, comment here.
So I would like to know which is the size of the radio source in terms of Schwarzschild radii, if you can tell us. Since you mentioned that there is 4 million solar masses in that region, which is the size of that region?
Well, the size is about 50-ish microarc seconds. Yeah, 50 microarc seconds. This is the size of the shadow, and this is, in fact, the radio emission seems to be even smaller than that. I mean, the example I always give, it's sort of a mustard seed New York scene from Rome. So that's what you can. You have that, I mean, you have proven technology that this actually you can achieve. Right? The only thing you have to do is now calibrate all the telescope well together that you actually turn this into an image rather than sort of, some rough structural information as we have right now.
Okay, let's thank Heino again.